Okay, we're going to finish section 4.4. We were looking at the Fundamental Theorem of Calculus. The part that's going to be important for us to remember for the next example is this theorem's definition. Okay, so the Fundamental Theorem of Calculus tells us that if we have the integral from a to b of a function, we can take the antiderivative, that's the capital F of x. We don't need to put plus c's, though you do on your gateway today, right? We don't need to put plus c's because they cancel out. And then we can evaluate it at the upper limit, evaluate it at the lower limit, and then find the difference between the two. And we're going to do an example of that with number 5. So this one is not set up with the antiderivative notation. We actually have to create the image that it's describing first. So this one says that we've got a region bounded by a couple of different equations that we're familiar with. What does the curve y equal x squared look like? Yeah, it's a parabola, right? It's our basic parabola, it goes through the origin. So we're going to sketch that to start with. Now, let me move this over here. This isn't working. Here we go. All right, so our basic curve looks like this. This is y equal x squared. What does the line x equal 2 look like? It's a line. Yeah, it's a vertical line, right, Jackson? Yeah, it's a vertical line over here at 2. So we'll mark off 2, 1, 2, and we have a vertical line there that we're going to go through, 2. So we'll put it in blue. So this is the equation x equal 2. And then the last one says the x-axis, so that's my horizontal axis, right? And I'll mark that one in green. What it wants is it wants us to find the area of the bounded region. So if you see all three of those particular equations, they create a space that is closed in, right? It's this little kind of triangular-ish shape here, and that's what we're trying to find the area of. So it's this space right here. So our goal is to actually create an integral that represents what's going on there. So our integral will start at what x value? 0, and it will end at what x value? 2. So those are my lower and upper limits of integration. Okay? The curve itself that we are beneath has what equation? X squared. And our variable that we're using, as typical for us, is dx. So all of these pieces matter in creating this equation, right, or this expression that we just wrote down. After that, we're going to use that fundamental theorem that we talked about at the beginning. So what's the antiderivative of x squared? All right, 1/3 x cubed or x cubed over 3. That's right, yeah. And then the fundamental theorem says I'm going to put a vertical bar at the end of this with the limits of integration on the top and the bottom. Okay, so when you get to a quiz on Monday, we are having a quiz over this on Monday. When you get to the test after Thanksgiving, right, this is the notation that I would expect to see written down. And then I would expect to see the step that shows you plugged the numbers in. So we would have 1/3 2 cubed minus 1/3 0 cubed. This, of course, is 0. This one is not worth our time to put in any calculator because it's just not a lot of arithmetic. 2 cubed is 8, and I've got times 1/3, so this is 8/3. Okay? Any questions on that? It's not a lot different than what we've done, but it's kind of merging two things. We merged the idea of creating a picture. We saw that happen in 4.2, I think it was. And we merged that with this fundamental theorem that we saw happen at the beginning of 4.4. All right, the last thing in this section is one more theorem. It's called the average value for integrals. So averages, as you know, right, if you were taking your average, let's say your test grades in this class, you'd add all your test grades together, and then you divide it by the number of test grades, right? Okay, so this is the same idea. Right here we have the antiderivative, right? We're going to be getting the antiderivative, the actual area under the curve. And the part at the beginning is averaging it over the interval where we found it from. So if you can imagine, I'll draw a picture of kind of what's happening here. We're just going to use the same equation that we just did, or at least I was attempting to. If I were to take this area and I were to sort of reposition it, and kind of imagine what happens with Play-Doh. You've got this shape. This isn't a perfect analogy because it's a three-dimensional object, but pretend the Play-Doh had no depth to it. Okay? It's thin. It's a real thin piece of paper, right? The Play-Doh. Or clay, if you're not familiar with Play-Doh. So you're going to take it and you're going to remold it. The amount of the Play-Doh doesn't change. It's still the shaded red part. You're just going to change how it's shaped. And you're going to change it into a rectangle. And the rectangle might look something like, say that. So this piece right here at the top gets repositioned over here, right, as we mold the Play-Doh. Okay, so this is what we're finding. We're finding this sort of vertical line that's in green that is the average height, so that the area underneath the green line is the same as the area underneath the curve. That's what we're doing when we're averaging these values, okay? So the process itself is really very straightforward. It's the same thing we've been doing, antiderivatives, and we have this little piece at the beginning that says, oh yeah, and I'm going to multiply it by this fraction. So the process itself is not difficult. So it says that we're going to find the average value of the function on the given interval, okay? So our interval goes from 4 to 9, so we're going to do our integral from 4 to 9. Our equation has the square root of x in it, and then dx. Now, if I want to find the antiderivative of this, which I do, I'm going to have to change the form of it, okay? Now, there's one more thing I need to do to this problem, because it says I want the average value. At the beginning, I have to do 1 divided by, and it's the interval's length. How far is it from 4 to 9? It's 5. I'm going to write it in as 9 minus 4, but feel free to just write it in as 1/5. I just don't want you to look back later and go, where did she get the 5 from? It's just the width of the interval, okay? So picture-wise, if you were looking at your calculator, here's what your calculator would look like. This graph itself is approximately like this. And we're going from 4 to 9 out here. This height would be 2 because the square root of 4 is 2. This height would be 3. The square root of 9 is 3. And we're finding, oh, that wasn't great. Let me move that just a little bit. I say that. Let's try again. Okay. We're going to be shading from here to here like this. And then we're finding that vertical line that reproportions all of the area to be a box, right? To be a rectangle. So what we're going to be finding is we're going to be finding something like that-ish, right? So that we end up with a rectangle with the same area as the red thing. That's a terrible rectangle. I apologize. The tools are not cooperating well. All right, so how could I rewrite the square root of x to be more helpful for the purposes of antiderivatives? Yep, x to the 1/2. Okay. It's good information to remember because you may see something like that on your quiz today, right? Yeah, it's definitely possible. All right, so how do I take the antiderivative of x to the 1/2? Or what is the antiderivative of x to the 1/2? Okay, so start with the new power. What's my new power going to be? 3/2. I need to add, so 3/2, x to the 3/2. And we'll divide by the new power, 3/2. We'll flip that in a minute. For the gateway purposes today, you could leave it like that with the plus c, of course. We have a 1/5 in front because that doesn't go away, and we need to evaluate 9 and 4. Okay, everybody good? Now, this doesn't look very nice, right? We don't want to leave it as dividing by a fraction when we're actually going to have to evaluate with it. That's not particularly friendly. So it'd be helpful for us to rewrite it with the reciprocal, 2/3, and to rewrite the x to the 3/2 as the square root of x cubed. Again, not necessary for your gateway today, but perhaps helpful as you're working through things later. So my fraction out front is 2/15. Thank you. All right, 2/15. And then I'm going to be plugging in 9 And while you're welcome to do 9 cubed and then take the square root, that's fine. You can actually do it in the other order, which would be easier. What is the square root of 9? 3, and then what's 3 cubed? 27. Okay, so I'm going to write this out, but that's what we're going to do. So we're going to doing the square root of 9 cubed minus the square root of 4 cubed. And the order, whether we do the square root or we do the cubing first, is irrelevant. So the square root part's the easier to do because it makes it smaller before it gets gigantic. So this one ends up being the square root of 9, which is 3. 3 cubed is 27. And do the same thing with 4. Square root of 4 is 2, and then 2 cubed is 8. So I have 27 minus 8, which is what? What is it? 19. And then 19 times 2/5 would be, 2/15 would be 38 over 15, which doesn't reduce. And it doesn't turn into a very nice decimal. It'll be a repeating decimal, so we don't want to have it in decimal form. Oh, good. That's what my notes say, too. It's always a good sign. Okay, any questions on that? So the step here at the end is very, very minorly different than everything we did before. It's just got this fraction in front. Okay, so when you see something with average value, highlight it, underline it, remind yourself that's the piece that we're adding on.